In this video, we're going to take a look at another type of problem that's associated with a differential equation and compare and contrast it with a type of problem that we've already solved. And we refer to those problems as initial value problems. And the new problems that we're going to take a look at in this video are referred to as boundary value problems, right? So initial value problems are often abbreviated IVP. And then boundary value problems are often abbreviated BVP, right? So first of all, we want to make it very clear as to what is the difference between these types of problems, and then how does the solution change, if at all, when we go from an initial value problem to a boundary value problem. All right. Now, so let me write down what we know up to this point, right? So we have our second order whole with constant coefficients, right? So they look like this. And now we know how to find the general solution of this differential equation, no matter what happens to the roots of our auxiliary equation, right? We have all three cases covered: the real, distinct, the real, repeated, and then the complex conjugate. But then now if we want to find, so from this, right, in fact let me write this, so from this we can find a general solution. Then now if we want to find a particular solution, we have to apply certain conditions. So let's just say applying certain conditions leads us to the particular solution. Now, so far, all the conditions that we've used, they have been of a specific type. And it was something that is kind of easy to overlook, because pretty much all the initial value problems that we've studied up to this point were of that form. Now, so let's define really what it is that characterizes an initial value problem, and then we will look at a different type of problem called the boundary value problem. So in these conditions, so if the value of the independent variable, right, of the independent variable is the same in all conditions, right? The conditions are referred to as initial conditions, right? So if the value of the independent variable is the same in all conditions, then the conditions are referred to as initial conditions. In other words, you know all the information that you need at a specific point, right? And we call those initial conditions, right? And we've seen them. We've seen initial conditions before, right? And what do they look like? So they might look like y of 0 equals 2. And then y prime of 0 is equal to 1/2, right? So these are initial conditions, because the independent variable here in both conditions has a value of 0, right? But it doesn't have to be 0. 0 is convenient, but it doesn't have to be. So you could have something like y of -2 is equal to 10, and y prime of -2, that's equal to pi, right? And you could have y of pi is equal to -2, and y prime of pi is equal to 10, right? So this would be one set of initial conditions, this would be another set of initial conditions, and this would be another set of initial conditions. And what defines an initial conditions is the fact that the number that I am boxing off here, those numbers are the same, right? That's what defines a set of initial conditions, right? But what if the numbers that I've boxed off here, what if both of them that I've highlighted in blue, what if they're different? Or what if I have different numbers in the green boxes or different numbers in the red boxes? That's what defines a boundary, a set of boundary conditions, right? So let's write this down. So if the value of the independent variable is different, right, in at least one pair, of conditions, the conditions are referred to as boundary conditions, right? So it basically, it's the, if you're using x as your independent variable, if the value of x is different in a pair of these, then you no longer have an initial value problem. You have a boundary value problem. So let me just, so for instance, if I take a look at this, so if I say that y of 0 is equal to 2, but then I say y prime of pi is equal to 1/2. Now I know one bit of information when my independent variable is 0, and then I know another bit of information when my independent variable is pi. So the fact that these are now different, right? The 0 and the pi are not the same, right? They still represent values of my independent variable, but not the same values of my independent variable. This would be an example of a pair of boundary conditions, right? But what's interesting about the boundary conditions also is that I don't have to know something about y and y prime. I could know something about y, like y of 0 is 2, and then I could know y of pi over 2 is -5. This would be another example of a boundary, a set of boundary conditions. Again, I know that my function has a value of 2 when my independent variable is 0, and my function has a value of -5 when my independent variable is pi over 2. And it's the fact that these two numbers are different, again, that define a boundary condition or a boundary value problem as opposed to an initial value problem. So another example would be something like this. I might know that y prime of 0 is 8, and then y prime of pi is the square root of 2. Again, I might not know something about the original function, but I might know something about its derivative, but at different points. So I know that the derivative has a value of 8 when my independent variable is 0, and also I know that the derivative has a value of the square root of 2 when my independent variable is equal to pi, right? So that's the formal definition or difference as far as we're concerned when we're looking at solutions to these ordinary linear differential equations, these second order wholeys, right? What characterizes an initial value problem is where at all the conditions the independent variable is the same. In a boundary value problem, the value of the independent variable is different in at least one pair, right? Now for us, we're just going to have a pair of conditions since we're working with second order differential equations. But if you go higher, it'll be the same thing. As long as you have a pair of conditions where the value of the independent variable is different, right? Then that's what defines a boundary value problem, right? Now, the thing about boundary value problem is this. If you remember, going back to the start of when we looked at the existence and uniqueness theorem, that theorem referred to specifically initial value problems. So for certain initial value problems, as long as the conditions of that theorem are satisfied, then we are guaranteed to have one and only one solution. There is no such theory, right, for BVPs, not in that general way, right? Now, boundary value problems, let's say this, you could make an entire course out of studying BVPs, and it gets pretty advanced pretty quickly. But for our purposes, we just want to be able to identify the difference between initial conditions and boundary conditions, and then know what are the possibilities when we try to solve for these boundary conditions. And unfortunately, BVPs, right, when you're solving boundary value problems, they may have no solution, unfortunately. That's pretty sad. Or we might be lucky and we get a unique solution. Right? Or we might actually end up with infinitely many solutions. Right? And this, what we call a trichotomy, right? Basically, something's a trichotomy if one of three things must be true, right? And we've seen this before. We've seen this in the context of linear systems, where linear systems can have no solution, a unique solution, or infinitely many solutions, right? The same thing is true for BVPs, right? Now, don't just take my word for it. Let's look at some examples, right? In fact, this is one example, but we're going to be looking at like several different conditions and seeing if we can satisfy them, based on what's given, right? So let's take a look at this example. Let's start with a very simple second order wholly. So let's say it looks like this, right? Okay, so let's write down, let's see if we can find the general solution, right? So the auxiliary equation, or the characteristic equation of this, is m squared plus 4 is equal to 0. So that's good. Now, if you look at this, you might say, well, there is no middle term. Well, it just means that the b is 0. So let's say you aren't quite sure how to factor this, and you want to use the quadratic equation. You can certainly do that. So it ends up being m is equal to, well, 0 plus or minus, and then you'll have the square root of 0 squared, and then minus 4 times a times c. So 4 times 1 times 4, and then this is all over 2a. So what happens here? Well, you're going to have 0 plus or minus the square root of negative 16 all over 2. So I'm going to stop writing the 0 and just do plus or minus, and then we're going to end up having 4i, and then this is all over 2, so we end up having plus or minus 2i. Now what does this mean about alpha and beta, right? So we can see that it's the complex case. We end up with the negative under our square root. That's because our discriminant in this case is a negative number. But what does it mean about the alpha and beta? Well, here, and maybe I should continue writing the 0, just for emphasis. We have a 0 there, we have a 0 there. And what this means is my alpha is 0, so the real part of the complex conjugates is 0, and then my beta is 2. And that's completely allowed, right? All right, so let's see what happens here, right? So let's write down our basis. And that consists of the function, so it's e to the alpha x cosine of beta x, and then e to the alpha x sine of beta x. And obviously e to the 0 works out nicely, that's just 1. So we end up with these two functions, again, which are clearly linearly independent. They're definitely not scalar multiples of each other. We end up having cosine of 2x and the sine of 2x, right? So then let's write down our general solution. So our general solution using our superposition principle, love that principle, it's y equals c1 times the cosine of 2x plus c2 times the sine of 2x. Right? So now, okay, that's good. So let's look at a few examples of BVPs now, these boundary value problems, to see if we can find a particular solution that would satisfy a pair of boundary conditions. And the first pair, let's take a look. Let's say we know that y of 0 is negative 2. And then suppose we know that y of pi over 4 is equal to 10, right? So again, these are boundary conditions because this number is different from this number, right? So these two numbers, because they're different, means that what we have is a boundary value problem, right? And let's see if we can find a particular solution. Right? We don't know if it will work or not, but we can try. Now, what's nice about this is both of these conditions involve y, so I don't even need to take a derivative here, right? So let's see. So when x is equal to 0, y is equal to negative 2. So what does that tell me? So if I plug 0 in, I'm going to end up with c1 times 1 plus c2 times 0. That's equal to negative 2. So right away, we get that c1 is equal to negative 2. Good. Let's apply the other condition now and say when x is equal to pi over 4, I know that y is equal to 10. So again, let's substitute those values into our general solution. So when x is equal to pi over 4, multiplying by 2 gives me pi over 2. The cosine of pi over 2 is 0, so I end up with c1 times 0 plus the sine of pi over 2 is 1, so I end up with c2 times 1. That's equal to 10. So we are able to find a unique pair of solutions, right? So c1 has to be negative 2, and c2 has to be 10. So we found a particular solution, and this is a unique particular solution is the function y equals negative 2 cosine of 2x plus 10 sine of 2x, right? So this BVP has a unique solution. All right. Let's look at a different pair of conditions, right? So let's say we have y of 0 is negative 2, and then y of 2 pi is negative 2. All right. So again, let me just write down, here's our general solution, so I don't have to keep scrolling up. So our general solution, remember, y is c1 cosine of 2x plus c2 sine of 2x. So this is saying that when x is equal to 0, y is equal to negative 2. Well, we know how this is going to play out. We just did it above, and we end up getting that c1 plus 0 is equal to negative 2. So right, so c1 is equal to negative 2. Let's see what the second condition is saying now. When x is equal to 2 pi, y is equal to negative 2. So again, now at 2 pi we have we end up having the cosine of 4 pi, which is still 1. And then the sine of 4 pi is still 0, and it's still negative 2. So what happens is I only have specified a value for C1. It doesn't give me any restriction, or it doesn't give me any more specificity about C2. So C2 remains a free variable. If you think of both of these right now as free variables in your general solution, even though we have two or a pair of boundary conditions here, right? The conditions only specify what must be true about C1. It doesn't specify anything about C2. So in this case, C2, again, it can still be any real number, but C1 has to be equal to 2. So because of this, we have infinitely many solutions to this boundary condition, or to these boundary conditions, or say it this way. So this BVP has infinitely many solutions, and they're all of this form. Y of x is equal to, so the only thing I can specify is what C1 has to be, but C2 can be any free variable, it can be any real number, right? So this is, similar to like when you're solving a linear system and you end up with a free variable, or what we call a parameter. In this case, we have one parameter here, and it can be, so essentially anything can be here as the coefficient of the sine function, but the coefficient of the cosine function must be negative 2. All right. So this is an example of where you can have a BVP that has infinitely many solutions. All right. Let's take a look at another pair. Let's take a look. So let's say now we have that the y of 0 is negative 2 and y of 2 pi is equal to 3. All right. Well, there's our general solution. So again, this is telling me the same thing as it did in the previous two pair of boundary conditions. So when x is equal to 0, y is equal to negative 2, and we end up getting that c1 plus 0 is equal to negative 2, which means c1 has to be negative 2. When I go to apply this condition now, when x is equal to 2 pi, y is equal to 3. So I end up getting that c1 plus 0 is equal to 3, or saying that c1 has to be equal to 3. This is a contradiction, right? So with a single pair of conditions, I can't have c1 being equal to two different numbers. So this is a red flag. It's a contradiction. So there is no particular solution of this differential equation that would satisfy these boundary conditions. And again, these are boundary conditions because these values of our x are different, right? So this BVP has no particular solution. Right? So it's just a matter of how the equations play out, and that this is why understanding, for instance, when a system or at least a pair of equations have no solution as opposed to having infinitely many solutions, or having a unique solution. Again, it's an important skill that we end up using in even a slightly different context, in the context of these boundary value problems, right? So hopefully, like I said, this is just a very brief look at the difference between initial conditions and boundary conditions, and hopefully these examples have shed some light on the concepts and some of the calculations that are involved. See you in the next video.